This video is brought to you by the volunteers from the Santa Fe Alliance for Science. This is the third one about Fibonacci and his numbers. This is about the number 0. Remember, Fibonacci lived in about 800 years ago in the city of Pisa in Italy. And in the previous videos, we learned about the number series, 1, 1, 2, 3, 5, 8, etc., where to find these numbers in nature, and also about the golden ratio, where you can find these numbers in ancient architecture. So Leonardo lived in Pisa, and Pisa was a city on the Mediterranean where they had lots of trade with all kinds of places all around the Mediterranean. Countries that are now in North Africa, in the Middle East, in Spain, all over, Greece. In particular, we'll come back to one city later, Algiers, which is now the capital of Algeria. So imagine Fibonacci goes to the market to buy some of the things that have been brought from faraway places. And the merchant says, okay, let's make up a bill. Let's see what you want to buy. Some bottles of olive oil, some sacks of grain, some bales of hay for your donkey. How many bottles of olive oil? You have 3 bottles. And they cost 6 lira per bottle. And the total is 3 times 6 is 18. 18. And you say, wait a minute, what are these numbers? These are I's, there's a V, an X, 3, 6, 18. What is he writing down? So he's writing in Roman numerals. Back in those days, they didn't write numbers the way we do. They used Roman numerals. Let's have a close look at what Roman numerals are and how they work. So let's count in Roman numerals. We'll count 1, 2, 3, 4. This is how we write them. 6, 7, 8, 9, 10, etc. So Roman numerals are like this. 1 is 1. It's the capital I on your keyboard. 2, I, 3, I. And of course you can go 10, I, but that gets very inconvenient. So you make up new ones. 5 is V. 6 is VI. 5 plus 1 is 6. 7, VII, etc. What about 4? 4 you can write like this. It's 5 minus 1. See, the 1 is on the left-hand side, meaning minus. So 8, VII, 10. Let's make up a new one. 10 is X. And how would you write 9? 9 is 10 minus 1. 11 is 10 plus 1, 10 plus 2 is 12, etc., etc. 20, let's write 20, is 2 times 10, XX. 21, XX plus 1. How about 19? 19, remember we start with 10 plus 9. How do we write 9? 10 minus 1, so here's 19. 30, on and on. Then when you get to 50, you can write XXXXXX, but that gets complicated. So 50 is a new letter, L, new symbol. 60, 50 plus 10, 71, 50 plus 10 is 60, plus 10 is 70, plus 1. And by the time you get to 100, there is a new symbol, 100. C. 500. A new symbol, D. 1,000. A new symbol, capital M. etc.
So that's how you write Roman numerals. But it is not very convenient. How do you write a million? How would you write 10 million? How do you do division? How do you do fractions? All that is very difficult to do with Roman numerals. So let's go back to Fibonacci. Now, Fibonacci's dad, Mr. Bonacci, was a diplomat. That means that a diplomat is someone who lives in a foreign country and makes sure that the relations between the two countries are good. So Fibonacci went with his father and ended up here in Algiers. At that time, the green part was a large Arab empire. In Europe, the development of science and math had pretty much come to a halt. But in the Arab world, science and math were flourishing. So when Fibonacci was in Algiers, he met with Arab mathematicians, and this is what he learned.
Remember, Fibonacci had numbers like this. For 1, he had I, and for 5, he used V, 10 is X, 50 is L, 100 is C, and on and on. As you go up, you have to make up new symbols for bigger and bigger numbers. When he sat down with the Arab mathematician, they wrote numbers very differently. They used different symbols, like this one. 1, 2, 3, the ones we would recognize. And Fibonacci said, oh, that's easy. If this stands for a 1, and that's a 2, and that's a 3, then this number stands for 1 plus 2 plus 3 is 6. And he said, no, that's not how it works. This is how it works. 1, 2, 3. This 3 stands for 3, but this 2 doesn't stand just for 2. It stands for 20. And this is not just a 1. It stands for 100. And the reason is that every time you go over one place, you multiply by 10, times 10. Then when you go over one more place, multiply again by times 10. So 10 times 10 is 100. And then if you go over one more place, that would be times 10 is the thousands. So this number doesn't read 1 plus 2 plus 3 is 6. It reads 123. This kind of system is called a place value system. Place value. Because the value of a number depends on where it is located. If it is located here, it's the ones, the tens, the hundreds, etc., etc. Now, notice that when you want to write a bigger number, you just add them to this side because it is times 10 times 10. You can make really big numbers without having to make up new symbols because the value is given by the place value system. One more thing, this is a place value system based on the number 10, base 10, called place value system base 10, and that's what we use. There is one more thing. Suppose you want to write down 100. That means I have to place it in the place of the hundreds. Here's the ones, here are the tens, here's the hundreds. So if I want to write down 100, I put a 1 here. Now, if I just write 1, nobody knows it's supposed to be 100. So you have to have a placeholder to say that these places are empty. So we put a 0 here, no tens, and no ones. So now the number reads 100. And this placeholder, the 0, of all the numbers that Fibonacci learned, the 0 is the most important one because it's a placeholder that allows you to put a number in a particular place and say that these places are empty. So 0 is the most important number that Fibonacci brought back with him from North Africa. So here are all the numbers and symbols that Fibonacci learned from his Arab mathematicians. 1, 2, 3, 4, 5, 6, 7, 8, 9, and the most important one, 0. These are the Arabic numerals. Let's talk about other number systems. Remember, our number system is called base 10. So if I write 123, that means that every time I go over 1, it's times 10. And I go over here, it's times 10 as the hundreds, etc. It's base 10. Why is it base 10? Well, probably because people started counting on their fingers, 10 fingers. What if you don't have 10 fingers? What if you're a computer and you run on electricity and all you can do is turn the electricity on or off or on? You only have 2 choices. Then you have to make a number system inside the computer that is base 2. So let's see how that works. So you have to write down numbers. Here's a bunch of numbers. And the first number stands for the ones. The next one is times 2, is 2. The next one times 2 is 4. The next one would be a value 8. This place would have value 16. This place would have value 32. And this place would have value 64. And on, every time times 2. So let's count up. How would you write 1 in a computer? Well, 1 is simple. You place a 1 in the 1 location right here. So this is 1. 2, you write here. There is a 2 here, and then the placeholder 1 0. 1 0 means 2. How about 3? 3 is 2 plus 1 is 3. 4. See, here's the 4, is the third location. 4 is 1 0 0. 5 is 4 plus 1 is 5. 4, 5, 6. 6 is 4 plus 2 plus 0 is 6. 7, 1, 1, 1. 1 plus 2 plus 4 plus 3 plus 1 is 7. And 8 goes over 1 place, and the important zeros is there. 1 0 0 is 8. And so on. So here's an exercise. By the way, this is called a base 2 number system. So computers work in a base 2 number system. Sometimes it's called binary number system, where the only numbers that exist are ones and zeros. Now, here's an exercise. Let's see if you can write down your age in binary. And I'll give you an example. My age is 67. 67. How would you write that in binary? So we have the 1s, the 2, 4, 8, 16, 32, 64, and so forth. So this is the 1, 2, 4, 8, 16, 32, 64. So I'm 67, so there is a 64. What's left over is 3. I have to make a 3. So a 3 I can make out of a 2 and a 1. And then 0, 0, 0, 0. So my age in the computer is 1, 0, 0, 0, 0, 1, 1. See if you can write down your age in binary. That's how computers work. So here is one last thing, money. Suppose something cost $1.27, and I say, okay, I do $1, 2 dimes, a nickel, and 2 pennies. Now Fibonacci would say, oh, I recognize that. $1 is like C, 100. Then the dimes are 10 each. A nickel is V, and a penny is I. 127. $1.27. So what do you think? Is our money system more like Roman numerals, or is it more like Arabic numerals, the way we normally write something? $1.27. What do you think?
So where can you find Roman numerals in our modern world? Well, here's one. At the end of every movie, where the credits roll and the names of all the people that have worked on a movie are listed, the year in which the movie is made is written in Roman numerals. Look at this one. MCMLXVIII. What year is that? Well, M is 1,000. Then there is another M with a C in front of it, so it's another 1,000 minus 100. Then there is L for 50, X is 10, V is 5, I. When I add them all up, it is 1968. Many old clocks have faces with the numbers 1 through 12 written in Roman numerals. And here's another one, the Super Bowl. Super Bowls are numbered in Roman numerals. This one is the logo for Super Bowl XXIX, that is 10, 20, 30, minus 1 is Super Bowl 29. Hi, that's it. I hope you learned something about numbers and different ways of writing them, and maybe something about Fibonacci, his dad, and the world as it was 1,000 years ago. See you next time.